Welcome back to Stats 2. In the lecture of today, we're going to discuss some of the essentials of linear modeling theory. So this is about linear models, from simple linear regressions to complex hierarchical models using mixed effects. What's like the underlying general theory behind them? What are some interesting concepts that we can introduce today, which will make our lives easier in working with such models mathematically? So as a start, let's think of a simple linear model, which is just a simple linear regression with one intercept and one slope for a single predictor. So how would we write down its formula? We could write, well, y is our outcome variable that is modeled as a function of, well, some intercept, which we can call beta 0, plus some slope, beta 1, times some predictor variable x, okay? And I could add a random like noise term here if I want to talk about the observed y, but let's say here this is about the predicted value for y. In that case, I don't need the residual error, right? Because this now describes my predicted value. So this formula is basically describing this classical kind of linear regression that I will have some estimate for the best fitting line for some data, which could look like this, for example. And this would have some particular intercept, beta 0, and some particular steepness, which would be represented by beta 1, in case this is my variable x and this is my variable y, like the predictor and the outcome. Now, this is a very simple case. What happens if I add more predictors to it? So let's say I don't have only one predictor, but I actually also have another predictor. Maybe we want to model reading times on some sentences as a function of relative clause type, and also, let's say, the age of the participant. So in that case, we would have one variable x, 1 maybe, which is about the relative clause type, and then we could have like another predictor, which is about some other predictor we want to consider. In that case, the age of the participant in years or something. So we would need another slope, beta 2, which would model the potential influence of age onto the output. And we can do this within the same model, right? We could even do things like consider the interaction between relative clause type and age, if that is like for some reason a meaningful thing that could be influencing the result even further. We could include beta 3, which will also, well, be actually multiplied with the product of x1 and x2. So the product of the values for the relative clause type and the age. And we could, in principle, make this model bigger and bigger and add more and more predictors. So we could also, I don't know, we could have a beta 4, which adds yet another predictor. Like there's no limit as to how big we can go. Like we could, in principle, add more and more predictors, and the formula would become larger and larger. But consider for a moment that despite the arbitrary number of parameters I can keep throwing at this model to make it bigger, there is some very simple general structure to how this term of values that are summed up here is composed. In the end of the day, each component of the sum is always one parameter, beta 0, beta 1, beta 2, beta 3, multiplied with some values, okay? Be it just a 1, that's kind of implicit here in the case of the intercept, or the values of my first predictor, or the values of my second predictor, or the values which are obtained as a result of multiplying the two predictors, which gives me the interaction, right? So in the end of the day, I always have some beta multiplied with some value. And now, looking back at what we talked about 2 weeks ago regarding matrices and matrix multiplication, can you guys think of like an elegant way to summarize this sum of many individual products into like very short notation that uses an operation that we introduced when we talked about matrices? Well, in fact, we can do this as follows. We can write that equivalent to what I wrote above here would be a similar equation, which is now using matrices, where I say on the left side I have a 1 by 1 matrix, in this case with just a single data point, which contains exactly this result yi, where I mean the predicted value and not the observed one, of course. So that's why I don't have the residual error term here, just as above. And then I say that this matrix, which is a 1 by 1 matrix, is actually obtained by computing a certain matrix multiplication. And can you guys guess what I multiply here? Well, on the left side, I would have a matrix which just has one row and which contains all of these like factors which are always to the right of a particular beta parameter in this sum here above. So for example, 1 for the intercept, or x1 for the first predictor, or x2 for the second predictor, or x1, x2, their product for the interaction, or x3 for yet another main effect predictor, and so on, right? So, okay, let's maybe consider this particular example where this is the entire model. In that case, I could write, okay, here I have the first beta parameter will be multiplied just with a 1. That's what happens in case of the intercept. And the second one, the beta 1, will be multiplied with x1 or xi1. And then you have xi2. That's the second predictor. Then you have their interaction for a change. So you have xi1 multiplied with xi2. And as the fifth, and here in this example, last element that goes into this matrix with a single row, you have another assumed like third predictor, its main effect. So you would just write xi3. And so this is our matrix on the left side. And on the right side, we have a column vector, which is just another name for a matrix that just has one column but multiple rows. And so can you guys guess what should go into this column vector? Well, we should just put the beta values in, right? So we could write beta 0, beta 1, beta 2, beta 3, and beta 4. In our particular example, that's all we have. And so, as you guys can see, on the left side, what kind of dimensions I have on this matrix? Well, I have 1 row and 5 columns, so that's a 1 by 5 matrix on the left. On the right, I have 5 rows, but only a single column, so I have a 5 by 1 matrix. And just a sanity check that I can multiply them, I have to look at the columns of the matrix on the left side and compare them to the number of rows on the matrix on the right side. And indeed, I see this is the same number, like 5 columns on the left and 5 rows on the right. So that's an indication that I can indeed multiply them. And so if you remember how matrix multiplication works, well, in this case, it would be rather trivial because the result, as we see here, is just a 1 by 1 matrix. And it would be the dot product of like considering this row as a vector and taking its dot product with this vector, okay? And that's exactly what we've written above here. So we take the first element in this row with the first element in this column, we multiply them together, that goes here. We take the second element of this row and the second element of this column, multiply them, this goes here, and we do this for all of them, and then each element in this row vector gets exactly one paired with one element from this column vector, and we obtain the exact sum that we've written above here, only that here we've just written it a bit more elegantly using matrices. And so this is still just describing the relationship for like one particular data point, but we can also extend this matrix multiplication to actually speak about concrete multiple data points. For example, let's start simple and say we have a data set that just contains 2 data points. That's not very much, obviously, but it's a start. And so we could represent this explicitly by saying, okay, we will have, instead of 1 row here on the result, we'll have 2 rows. And so instead of writing abstractly yi, I'm now completely going to write that I have like one y value for the first data point and one y value for the second data point. And if I do this, I will also have to add another row here on this matrix multiplication on the left side. So now everywhere where I wrote I here, I will say, okay, the first row is about the first data point and the second row is about the second data point. So I might as well write x1, 1 and x1, 2 and x1, 1 and x1, 2 and x1, 3 in the first row. And just by analogy, I would then, for the second data point, write, okay, so this is now, again, 1 stays the same for the intercept, and here I will have x2, 1 now, because that's the second data point. Here I'll have x2, 2, and x2, 1 multiplied with x2, 2. And lastly, x2, 3, okay? And so what happens now is the matrix multiplication still works, only that here on the left side, I now have a 2 by 5 matrix, right? And thus, I will have as a result now a 2 by 1 matrix. And we can extend this in principle not just to 2 data points, but we could also represent our entire data set of like not just 1 or 2, but maybe 3 or 4 or 10 or 100 or 5,000 data points just by adding another row to this matrix on the left here for each data point. And this will always also correspond to one unique y value, like value of the predicted variable, of the outcome variable, here on the left side of this equation. So the most general thing we could do for this particular model, for this particular linear model, would be to say, okay, we have some unspecified number of rows, which we can call n here, which is like the number of data points. So this will go all the way up to yn, and now this will be all the resulting predicted values. And then here we also will have exactly this number of values for each predictor, or like for each interaction constructed from some predictors. So here we would also go all the way with all of these values up until we reach the nth row, which represents the nth data point, which will then be, could be written as follows. And each time the matrix multiplication will still work because the number of columns doesn't change, right? And the number of columns has to match the number of rows of the matrix to the right. So xn1, xn2, and finally xn3, when we think about this particular model with 2 main effect predictors, 1 interaction, 1 further main effect predictor, and an intercept. That's the most general thing we could write about this model. Obviously, we maybe shift the matrix down here to make it a bit more pretty, maybe. And okay, so looking at this, maybe you're not yet convinced that this is kind of making things easier for us, because, okay, if we write these matrices down, it looks much more cluttered than the simple and intuitive equation that we had written above here. But things start to get interesting once you like don't write this matrix in detail explicitly, but just like give each of these matrices in this multiplication equation a certain name, okay? So instead of writing this explicitly as the matrix with, well, containing y1, y2, and up until yn predicted values, I could just call this entire thing a name, right? I could call this entire thing capital Y, for example, right? And I could say this capital Y is equal to a matrix multiplication, where on the left side I have this matrix, which I could call capital X, okay? And then this will be multiplied by a matrix, actually like a single column matrix, a column vector, which I could just call in general beta, okay? Where beta, so beta is equal to this thing, and X, capital X, is this entire matrix in the middle here, and capital Y is what I have here on the left. So notice that now I have just a very simple equation with just 3 variables, only that, well, they actually represent what I have spelled out here. So y is the vector of all the predicted values, and x is the vector containing the same number of rows as y, but the number of columns will be the number of parameters that it represents, basically. In this case, an intercept parameter, 3 main effect parameters, and 1 interaction parameter. And the beta matrix will be a matrix that is just one column and contains all the individual beta parameters, beta 0, beta 1, beta 2, beta 3, up until beta 4 in this example, that we want to estimate if we fit such a model. And so just take a moment to appreciate that this simple summary of saying, okay, well, in this case, predicted value for the outcome variable, that can just be summarized with this simple matrix multiplication. Regardless of how many data points I have, this will basically be sort of giving you an answer for all the data points from the first one to the nth one. And you can also keep adding, in principle, more parameters here, and maybe do a three-way interaction between x1, x2, and x3, let's say, or yet another fixed effect. So yet another fixed effect could be plus beta 6 times some further predictor. So this is whatever I would add here, I could just easily represent this as further columns in this beta vector, aka further rows in this beta vector, aka further columns in this x vector. And this general summary, that in the end it's just a simple matrix multiplication of, well, x times beta, that remains true for any linear model. That's why we call this way of sort of writing the linear model down in matrix notation the general linear model, because it's not just about some particular linear model with so-and-so number of predictors, but it is a simple, general, and elegant way to write down any linear model mathematically as just one simple, unchanging matrix multiplication. Okay? So that's the general linear model in matrix form. So just looking at this, you might ask yourself, okay, well, here in this equation, y, the predicted values are on the left side, but wouldn't it be more interesting or sensible to have an equation where beta is on the left side and everything else on the right side? Because the values for these beta parameters is actually what I usually don't have and want to find in order to be able to then generate predicted values in the first place. So is there a way to write this equation in another way where beta is on the left side and everything else is on the right side? Well, if we had some inverse matrix of x, then our lives would be nice, right? So we could say we multiply both of these terms, both the left term and the right term, from the left with some inverse matrix of x. So x to the power of -1 is a notation, so x inverse times y, matrix multiplied, that is equal to inverse of x multiplied with x multiplied with the beta matrix. And then this would further simplify to just saying, okay, what is x? Okay, x inverse times y stays the same, but what happens on this side here? Well, these two cancel out, right? So this x inverse multiplied with x will just be the identity, and the identity multiplied with beta will just be beta, okay? So just swapping around the sides of the equation, I could then write this to the left, so say beta can be obtained by multiplying the inverse of the matrix x, if we can find such an inverse, with y, okay? And this way we have now rearranged this equality, but with respect to beta, to the matrix that contains all the individual parameter values for intercepts or slopes. If you paid close attention in the lecture on matrices, you might think, oh no, we are screwed, because the inverse is only something I can compute with a square matrix, right? With a 2x2 or 3x3 or 4x4. But who tells me that the number of parameters here is exactly the same as the number of data points? That would be a very rare case, actually, right? usually you have much more data points and parameters. And so this matrix X wouldn't be a square matrix. So what can we do? Are we stuck here? Like, can't we compute the inverse now? So we can't really solve this for beta? Well, one detail I didn't tell you in the matrices lecture 2 weeks ago was that there is a sort of generalization of the inverse concept, which also applies to non-square matrices, okay? We don't have to go into the details of how we can find such like generalized inverses that also can be found for non-square matrices. Just so you know that like the most common one that we typically want to compute in case of a non-square matrix is the so-called Moore-Penrose generalized inverse. Okay, so in case of a non-square matrix, just compute the Moore-Penrose generalized inverse. R can do this for us, so no worries. And this will also allow us to compute the inverse we need in this equation in case our X is not a square matrix, which is actually going to happen most of the time. All right, so with these ideas in mind, let's maybe see a concrete example in R of how we can find the generalized inverse of a non-square matrix and then go on to like multiply this with some matrix of outcome values y and see how this will just elegantly give us a matrix of the resulting beta values. All right, so we've opened up our studio here on the left side, and let's maybe define a matrix y first, which for simplicity will just have it contain 2 data points, okay? So it could be more data points, but let's say we are starting simple. We're looking at a very simple example with very small number of data points, and so y will be a matrix which contains exactly the values, let's say 4 and 2, and yeah, and we have to specify the dimensions, so it will have 2 rows and 1 column. Oops. So that can be validated. So we see here, this is indeed our matrix Y now. And our matrix X will be a matrix which, for the sake of like an interesting example, we could have maybe 1, 2, 3, 4, 5, maybe 6 rows. So let's add another one. So like 6 rows, like could pertain to some, well, one of them will be the intercept maybe of the linear model, and the other ones could be either main effect or interaction slopes, okay? So we're gonna say this matrix will have the values as defined by this vector, which will be maybe 1, 9, 7, 2, 3, and 4 in the first row. In the second row it will be 1, 8, 3, 6, 8, and 10. Okay, so this is like the first row is the first data point, the second row is the second data point. Now, as we've specified these by row and not by column, the matrix function in R will also require us to set this argument by row to true, which is not the case by default, so by row should be true. And of course I shouldn't forget to specify as like the second and third positional arguments the number of dimensions that this matrix should have, so 2 rows and 6 columns, so 2 and 6. And with these arguments, we are ready to create this matrix. We can validate that it's indeed the matrix we had in mind. So maybe make this a bit bigger for us to be able to see. So maybe move it up a bit. So yeah, it's not perfectly visible, but you guys get the idea. So it's indeed this matrix with 6 columns. Maybe put it out again. So this matrix right here. And once we specified it like this, we are now ready to try to first find its inverse and then next do this matrix multiplication with the matrix Y and see what beta matrix comes out. In order to find this so-called generalized inverse of a matrix in R, we can use the functionginf, so written like this, ginf. But before we can use it, we actually have to load the library which contains this function, namely the library mass or MASS, all capital. If you haven't installed it, you should like do install packages first, of course. Once we've done this, we can compute the inverse, or actually, well, the generalized inverse for non-square matrices based on the Moore-Penrose method. using this function ginf, which is like similar to solve. I believe you could even maybe do it with solve and it would give you the same results, but ginf will definitely give you this kind of generalized inverse. And so we give it x, and that's how we compute the inverse of x. And so the inverse of x, as you can see here, is a matrix with, well, you can't see it too well here. Let me put it out again. Oh, that's x, and the inverse of x is a matrix with 2 columns and 6 rows. So x original is a matrix with is a 2 by 6 matrix, and its generalized inverse will be a 6 by 2 matrix. Okay, and we can also sanity check what, for example, x matrix multiplied with its inverse is. Well, it's the identity matrix, the 2 by 2 identity matrix pretty much, and the other way around we would see a rather puzzling result actually. So you might think that here you would now get the 6 by 6 identity matrix. Well, in fact, let me tell you that we're actually getting something slightly odd looking, which is a 6 by 6 matrix. So now this is like the 6 columns printed out, but you see this is not the diagonal 6 like the I6 identity matrix, which would look like this. So you might wonder, okay, if this is not the identity in some cases where we are dealing with this kind of strange generalization of the inverse to non-square matrices, will this still work? Like, will this still be the case that multiplying this matrix x inverse times x, which if it isn't the identity, with this beta matrix, will this still be equal to beta? Well, it turns out that for these kinds of equations, where now like solve the equation for beta, and then I compute beta as like this pseudo x inverse times y, it will still work, as we will see. Okay, so let me just show you why we can still work with that, even though this is some kind of pseudo identity matrix, which is not the real identity matrix which would work always. But here in this kind of equation, it will work just fine. So this tells us that we can compute the beta matrix as a multiplication of this pseudo inverse or like generalized inverse in x with the matrix y. Okay, so we have created that. Let us look at beta. So beta is now this matrix, which, well, here in this example it's 5. In our example in R it's now 6 values, so which contains 6 different values like beta 0, beta 1, beta 2, beta 3, beta 4, beta 5. And here we could now sanity check if, okay, well, if we take this inverse matrix x times x, if this sort of pseudo-identity matrix, even though it's not the real identity matrix, will still reproduce beta here, which allows us to basically cancel this out and just write beta. So just to confirm this, we can see indeed that's all the same. So it's kind of weird. So we can multiply this matrix, which is not really the identity, with beta, and it will still give us beta as a result. We could also have multiplied, of course, the real identity matrix for the 6 dimensions with beta, and that would also have given us beta. So here just is an interesting example for matrix algebra, that sometimes having something in a matrix multiplication on the right, which is known, and on the left, which is unknown, there could be multiple solutions for it. So there could either be the real identity matrix for 6 dimensions, or there could be the product from the matrix multiplication of this Moore-Penrose pseudo-inverse of x times x. Okay, so just a minor tangent, but so that you're not confused in case you control this or you check this and you see that actually this product of matrices pseudo-inverse x with x is not always the identity matrix. It will still work for such matrices as we see here for this beta that we've derived by canceling these terms out. All right. Now the last thing we want to sanity check is if we compute this multiplication here, like x with beta, with the beta we have derived here, if this will give us y back, which should be the case, right? For this to be like equivalent to that equation here. So you'll write x multiplied with beta, and this gives us 4, 2, and that's indeed our original matrix y, also containing the values 4 and 2, which, well, contained our outcome values, right? if you think about what we just did here, it's actually a bit strange. So we started off defining the outcome values y, and we picked 4 and 2, but I guarantee you we could have picked any values. I didn't cherry pick them, and this procedure would still work. And then we went on to take this matrix X containing our parameters, and also with each row representing a distinct data point. And we computed the generalized inverse of that, then multiplied the generalized inverse with this y that we pre-specified, and then we got a matrix beta, which is like a vector containing the parameter values that we should have for beta 0, beta 1, beta 2, and so on, up until beta 6 in this case. And just by doing this, magically, we found such an optimal selection of beta values that if we took our matrix X and multiplied it with beta, we would get out exactly the original Y, so the values 4 and 2. And that's strange because, well, this is kind of like running the regression, right, and finding beta. And here we happen to be able to find such a good selection of beta values that we even get exactly the values that we gave in terms of y. Okay, so in this case, there is strangely no distinction between the observed y values and the predicted y values. Like, we can run this regression sort of and find beta values, beta coefficients, beta 0 up until beta 6. And interestingly, we are able to exactly reproduce the y data. So the y predicted will be exactly the same as the y observed in this case. Now, the reason why this is happening here is that here we are in a kind of strange or like unusual situation compared to a real-world example. So in a real-world example, we would have a lot of data points, certainly more data points than we have parameters. But here in this toy example, we actually have, if you look at the dimensions of this matrix X, you can see that we have the rows are the number of data points, and here we just had 2, okay? So there were two rows of the matrix Y and 2 rows of the matrix X in this example in R here. So 2 data points, but 1, 2, 3, 4, 5, 6 parameters. If you think of the dimensions of this matrix X, which is, by the way, also sometimes called the model or design matrix in the context of the linear modeling theory. So if the model or design matrix, which is said to have n rows and p columns, where n represents the number of data points and p the number of parameters, in a case where, so let's distinguish certain cases. So if we have n, the number of data points being smaller than the number of parameters, as in this toy example, in that case, we're saying that this is an over-parameterized model. An over-parameterized model is basically what happened here on the right side. And the interesting thing about an over-parameterized model is that you can always find an exact solution. So you can always find a selection of betas, beta coefficients, beta 0 up to beta, for example, 6 in this case, which once you multiply X with that beta matrix, you will get exactly the observed Y values. So here you can always find an exact solution. And in fact, there are even infinitely many exact solutions. So actually, I mean, you can't see this in this output here, but I'm telling you that these 6 beta values are not unique. There are also other possible selections of 6 beta values, which would also have satisfied this equation here. So this is the situation when we have an over-parameterized model, where we have more parameters than data points. Then we can always fit the data perfectly, even with like multiple possible, infinitely many solutions. But the real-world case is obviously the case where we have at least as many data points as parameters. And so that would be, you could write that as the fact that n is then greater or equal to p. And so if that is the case, then we're not over-parameterized anymore. That's usually the situation that we are dealing with, like when we are actually trying to fit a model to data, then we usually have like maybe, let's say, 100 data points, but like 3 or 4 or 5 parameters. So usually n is and should be much greater than the number of parameters. Otherwise, the parameters will just overfit or like even perfectly fit the model in the case of the over-parameterized situation. So this is like the real world situation where you have many data points but only a few parameters. For example, as we said, 1, 2 main effects, the intercept, and an interaction maybe. So each beta with some number is one parameter, okay? And in this real world case, finding the betas is now an approximate enterprise, okay? So while in the toy example where we are over-parameterized, we can find a selection of beta coefficients saved in this beta matrix, which exactly fulfills this equation if y now is the observed y, okay? But once we are in the real world and we are looking at a lot of data points and only a few parameters, then it would be a very exceptional and rare, almost impossible situation to have a linear regression, let's say, where we have some real observed data points, and magically we can represent them in a straight line where each of them lies exactly on the line. Like this will never happen. It could in principle happen, but it will be the very rare exception, okay? The usual situation is we have some data points. I'm just showing like one particular predictor here, but it's all the same for any other predictor. And the idea would be that we can find the approximately best solution. So we can find the particular beta 0, which represents the intercept here, and the particular beta 1, which represents the slope, in such a way that this line, as we mentioned in some of the introductory lectures, minimizes the sum of squared residuals here, okay? And so then we can find a certain beta matrix, but which will not satisfy this equation exactly. Instead, it will only satisfy it approximately. And this approximateness is represented by this usual error term that I've now left out here for simplicity, namely the fact that here we always add this epsilon, which is assumed to be like random noise, which is not explained by the linear relationship. That's exactly, whatever residual there is for each particular data point. So here I could have this epsilon here, and likewise I would now also have to add it everywhere else, okay? So also note that now we're not talking about the predicted values for y anymore, but actually about observed values, which might not exactly be the same as the predicted values by a linear model, okay? So this is now the observed y, and we would then have to say, let me make some space here. So instead of just having the betas which are added, we are now adding an entire vector of error terms as well. So I just make this a little bit thinner. Whoopsie. So plus, and then here vector. So here again I will have beta 0, beta 1, beta 2, beta 3, and beta 4. And now here I will have the residual terms for each data point. So epsilon 1 is maybe this residual, and epsilon 2 is this one, epsilon 3 is this one, and so on, right? So each data point gets their own residual term. And likewise, I could summarize these residual terms as like one matrix of residual terms, which I could call just epsilon, okay? And so I could write here, this should always have a plus epsilon, maybe write it a bit prettier, plus epsilon, which is now the matrix of, residual terms. So that is how we would have to write the linear model equation, the general one, in case we are also considering this, real world scenario where we only can approximately find a solution to this equation y equal x times beta. And so this approximateness is represented by now adding this error term here, which now in this case, in this matrix form, is like this actual entire column vector, like a single column matrix, which contains the residual for each individual data point, which is also graphically represented here, right? So this is the idea. And in fact, based on this distinction of like being able to find an exact solution as in these over-parameterized situations that we saw here in R, versus the actually more realistic situations where we can't find an exact solution. We can also speak of this in terms of deterministic versus non-deterministic functions. So let's see now what that means. A deterministic function is basically a function that if you give it some input, it will always give you an exact output as a result. Like it will always give you the same output no matter what. For example, a simple linear regression defined as a deterministic function could look as follows. So we could say, let's say we have one intercept, beta 0, and one slope, beta 1, okay? And so we can model our outcome variable y as this function, which I may call phi, okay? That's my function, and it takes certain arguments. So it takes the data x as an argument. It will take the values for beta 0 and beta 1, which I summarize as just one matrix beta. And it will, well, and that's it basically. So we take these values, and as a result, it will spit out basically beta 0 plus beta 1 times x, okay? And here, well, just remember that beta is now my matrix containing or summarizing beta 0 and beta 1. Now this is deterministic because if I have my data, which are fixed, and I also have some candidate values for beta 0 and beta 1, in that case, I am guaranteed to always get the same result. You can kind of think of it like the predicted y value, right? So just think of this as like the predicted y value of a linear model. That is deterministic, of course. Once I have the fitted parameters and I want to make a prediction for a certain data point, and I have my predictor variables values given, then it's deterministic. I will always get the same result. But at least in these real world cases with tons of data, but only a few parameters, the observed data are actually modeled by a non-deterministic function. Now what do we mean by that? So for a non-deterministic function, we would kind of make this adjustment you also just saw being made here on the right side. So a non-deterministic function for a simple linear regression would say, okay, my data y, which is now actually about the observed data y, okay, not the predicted one, that is equal to, again, some function phi maybe, but this function now takes 3 arguments, so it could take the argument, again, x, our data, and beta, which is our like summary of intercept and slope parameters, but it will also take, as we said, this error term epsilon, okay? And now this will be equal to beta 0 plus beta 1 x plus epsilon, and the crucial thing that makes it non-deterministic is how we define epsilon. So here we say that epsilon is a random variable that is sampled from a normal distribution with mean 0 and some standard deviation sigma, okay? And so now it's a different game, because now each time I give this function the same arguments, I might get something different out of it, okay? So even if I have beta 0 fixed and beta 1 fixed, and also my predictor data x are already given and they don't change, because of the epsilon, I've now introduced randomness, okay? Because now it says, okay, there will be data generated from this which roughly resemble what this deterministic term represents, but with a caveat, with a non-deterministic caveat basically, that we are adding this residual error, which is randomly generated each time we are asking the function to give us an output value. And so this is like a model of the data generative process that would generate something like this, for example. Okay, so if it was deterministic, we would always expect to find something exactly on this line. That would also be what our best fitting line, aka our predicted y values, look like. But we say our observed y values actually come from such a non-deterministic process, like a non-deterministic function, where yes, we have this linear relationship, but we also have these residuals. And these residuals come precisely from some normal distribution with some standard deviation sigma. Okay, so that's the difference between the deterministic and the non-deterministic function, and how each of them can represent either the predicted or the observed outcome values in a linear model. All right, so here we're just left with the bare essentials on the board. So we made some space, and now we have time to see some examples maybe in R using real data sets to really think this through, like how would our model, our design matrix look like. Let's open up RStudio and see what we can do on a real data set. All right, so within RStudio, we can now load this data set that you may remember from one of the previous lectures, which was about the relationship between pathological, psychological symptom score predicted by stress level, which was actually from a real study by Howell and just Howell, 2011. And it's in our data folder again, so we can just load it into R using this command here, read table data stress symptoms.txt with the header true specification. And now let's inspect our data set, which has, as we remember, these columns. So the participant column indicating the ID of the particular participant, the stress level score, and the psychological symptom score. Okay. And now let's fit our usual linear regression here again. So we could say we want to save it as model M1 using the LM function, and our DV is the symptoms. Our predictor, our only predictor, is the stress level. But okay, to make it explicit, I will write 1 plus stress because we are also predicting an intercept. But this, okay, just to be clear, this and this have the same effect. Just this is a bit more explicit about also including an intercept parameter, like both mean the same thing. Data will be our data frame here with the stress symptoms data. We're fitting this model, and we can, as we usually do, also print a summary. A summary of this model. And here we have our usual output, right? So we have the intercept, the slope, and with the summary output we also get this like inbuilt t-test in the linear model, where you can also see some t-value and p-value, which is about the specific predictors here. So either the intercept, okay, it's not really a predictor, but it's a parameter. So the average basically psychological symptom score, and then you have here an estimate for the slope of the stress predictor, which is significant as well here, right? So there seems to be indeed a significant relation between the stress level and the psychological symptoms. Now, why are we doing this? Because I want to show you real quick how we can extract the so-called model matrix, like this X in our general linear model here. And in fact, in R, there is this function called model.matrix, okay, which allows us to access the model matrix underlying the regression that was fit in using this linear modeling command LM. Okay, so we can use model.matrix and provided our fitted model, so M1 in this case. Let me save this as maybe mmat1, okay, model matrix 1, and I can now inspect this. This is just like another long matrix or data set which contains our model matrix. And so in this case, here we see the first six rows of this matrix. You can see that it has the structure of like first column, just as in our example on the board, is just like ones because that represents the intercept. So like imagine that you would have then this matrix multiplied with some with these two parameters beta 0 and beta 1. Okay, so now all the beta zeros will get multiplied, the beta 0 would get multiplied with all the ones here, and the beta 1 multiplied with all the values of stress, okay? And this entire thing is like a matrix, okay? So that's the matrix here, and it goes on and on. We are only looking at the first 6 lines, and likewise here, like it starts basically, okay? And we can also see how many rows this matrix has, so just two columns, right? Because we just have two parameters, the intercept and the slope predictor. The intercept always gets the 1 as a value by default, and this always has the values of our variable stress, like the actual stress level scores. That's what's going to be here in the matrix. And we can also check how many rows it has. So let me delete this first, maybe. So using the n row command, we can apply this to our matrix. And we see that there are 107 entries, which means that there are 107 data points overall, right? So 107 data points. Right, so here we can basically extract this kind of theoretical mathematical structure, like this model matrix or design matrix, as we sometimes call it, from a fitted linear modeling object in R. Now, another example is a very similar data set, which is called, well, the file is called stress symptoms 2, which is from a study with a similar research objective, only that here we now have a further variable. So here we now also have not only the stress and the symptoms, but also categorical predictor, gender in this case. We can actually, I mean, we maybe want to code it as a factor. So let's say stress symptom gender shall be equal to as factor of this variable, which is for now just coded as simple strings, okay? And you can see what the default contrasts will be. As you can guess, it will just be, oops, sorry, I should have, of course, indicated the variable. So it will just code them as 0 and 1 going alphabetically. So man is now 0 and woman is 1. So, okay, let's just leave it like this for now. And we can now fit our linear model where we say we want to predict the symptoms as a function, as a function of stress plus gender, and use our data set. I've now actually overwritten the old variable, so stress symptom for me here now contains the new data set that also has the gender variable, okay? You might also call the stress sim 2 maybe if you reproduce this, but anyway, okay? So this is our model 2, and we can again maybe see the summary. As you guys should know by now, the way to interpret this slope is that here that represents the change between the stress level going from male to female participants. So it's just a small change of 1.57, and like there's no significant effect associated with it, so gender doesn't seem to play a role here. And also, like, because it's treatment coding, as you know, the intercept will just represent the level for the baseline, so for men, and then you have to add the slope to get the predicted average for women, okay? That's just based on the contrast coding we use here. So with this model as well, here we have 3 parameters. So we expect, of course, that our model matrix will now also have 3 columns, right? One for the intercept, one for the first slope, one for the second slope. Let's verify that, okay? So we could have a look here. So we're gonna do again mmat2. We want to save the model matrix, matrix of our M2 model. Let's see the first couple of entries. Maybe show me the first 10 couple of entries for a change. And indeed, what we see here is we have 3 columns, right? So we have the intercept, the intercept, which always gets the 1, obviously. We have the stress levels, and then we have here the gender, which would be 1 for woman or 0 for man. Here the first 10 entries happen to be all women. That's why we only see ones here, but maybe if we go to the tail of the data set, we would see something else. Okay, yeah, so the last 10 data points, they are all pertaining to like some male participants. So here we get a 0 on this gender woman predictor. And yeah, so this corresponds to our beta 0 now, the intercept, this to our beta 1, the first main effect slope, and this to our beta 2, the second main effect slope. Now, obviously, we could also have an interaction, right? We could also say we want to refit this model, but now maybe using the interaction also between stress and gender. So we will have stress main effect, gender main effect, and the interaction between the two. Let me call this M3 maybe. And if we create the model matrix of this, we would then see also that we have another column, right? So if we do this, we get model.matrix of M3. And let's again print out maybe the first 10 entries of this. So indeed, you see now that there is a further column to the right. Now, this interaction will, as is always with the case with interactions, you have to multiply the value of one predictor and the other. So here you would have to multiply this value with this value to get the value that the interaction parameter, or the interaction data has here, basically. So here it will just copy this value because 30 times 1 is 30. But if you go to the tail, you should find that all of the values are 0, right? Because men are coded as 0. So if you go to tail, then you would see this accordingly, right? So here the interaction data input always is a 0 because it's derived by basically taking this times this, which obviously will be 0, right? But as you can see now, we would have beta 0, beta 1, beta 2, and another beta 3. So our model matrix now has these 4 different columns. Now, one last thing we can try, one last variation would be to change the contrast coding. So now let's say, as opposed to having as the treatment coding, let's maybe go for something else, for example, sum coding. So let's do the scale sum coding where we code the factors as minus 0.5 and 0.5, at least for a balanced data set. That's quite sensible because then the intercept can be interpreted as the average, but we still have the slope representing the overall effect magnitude, right? So let's try this and now maybe do one final model. So let's call it M4, which will now be based on our sum coding, also including the interaction between the two parameters. And again, we want to have a corresponding model matrix. So let's extract this from our M4 variable. And if we now see the first entries of this, we can see here very clearly what happened, right? So we have again the intercept, the stress level values, the gender values, which now 0.5 is the woman and minus 0.5 would be the man level. And here you can see how now the data for the interaction come, how they are derived. So it's just like taking 30 times 0.5, that will be the interaction value now, okay? And 27 times 0.5 will be 13.5. Likewise, if you go to the very end of the data of the model matrix, you will see that accordingly for the men who are coded as minus 0.5, you get this kind of coding, right? 22 times minus 0.5 will give us this interaction data value of minus 11. So here you can see how the model matrix will also have like somewhat different entries depending on the contrast coding of our categorical predictor. But the overall story is clear, right? So we will always have the number of columns in the model matrix representing our number of parameters, like intercepts or slopes, that we have in our linear model, and the number of rows is always the number of data points that we have, okay? Okay, so we've seen how to extract the model matrix, also called design matrix, from a fitted linear model object in R. One last thing to clarify about the notation regarding the model matrix that we use and that you also sometimes will see in the lecture notes, for example, is that sometimes you'll see that it says this model matrix is also, or is kind of derived by applying some function f on the data x and taking the transpose of that. Now, what this means basically is that if you imagine that you have your data, for example, well, your just data set with two predictors like the DV and then the predictor 1 and predictor 2 could be like psychological symptoms, stress level, and gender, let's say. And then this thing is your data y, your outcome data, and these two columns are your data x. And given this, there are still multiple possible linear models you could fit using this data. Okay, so let's say maybe here are some data like 30, 51, Here you have maybe 0.5, minus 0.5, and so on. And here you have, let's say, 20, 26, and you can imagine the rest. Okay, so just our possible data we could have, and there are multiple things you could do. You could say, I'm just writing Elmer syntax now. What you could do is either to take the DV and model it as a function of just an intercept, right? That would be valid if you would neglect the data that are in X at all. Or you could say, okay, I want the intercept and the main effects of the two predictors, but I don't want their interaction. Or you could say, no, I actually also want their interaction. And then you would have like the full possible model that you could fit. Or you could do something and say, oh, I want to like only fit or let's say I'm pretty sure that the average overall is on 0, so I already know that I don't have to estimate an intercept, so I'm explicitly going to say I'm not estimating the intercept at all, right? Then I would one would have one parameter less, but I could still fit anything else, right? So in principle, there are many possible models I could fit, or for example, a model that estimates the intercept and the interaction, but no main effect. So it would assume that there is no overall effect of either of the two factors, but that they still interact somehow. So all of this is possible, right? And who tells me just that having these data, which model I should fit, right? Or like, and depending on which model I fit, my model matrix or design matrix will also look different, right? So here I have one parameter, so the model matrix will have one column, just full of ones. Here I have 3 parameters, so the model matrix will have 3 columns. Here I have 1, 2, 3, 4 parameters. Here I just have 3 because the intercept is fixed at 0, so it's not a parameter anymore. And here I have 2 parameters, right? And so what this notation just means is that you have like this sort of selecting function, which given the data, which given this X data, will basically take the data, and in case of, for example, this model 1 plus P1 plus P2, so if that is your fixed effect structure, then f of x would create this kind of matrix where you have the 3 rows now. So the first row is now the intercept. So let me just put 2 entries maybe. The second row would be 20 and then 26, 20, 26, and so on. And the third row would be 0.5, minus 0.5, and so on. But if you had another case, for example, let's say you wanted to fit just the intercept model, okay? Or, well, okay, let's try that maybe. In that case, you would have just f of x would be equal to this single row matrix with just ones in it, but nothing else. Very trivial kind of thing you would do. You would completely ignore the data, right? So depending on which of these possible effect structures you pick, you would also have a different selecting function that selects the data out of it. Or like last example, let's say you want to have the interaction as well. So you would say, I want to do P1 plus P2 plus P1, P2 interaction. Well, in that case, you would have to add this further row. And then you would have, what is it, 20 times 0.5 is 10, and 26 times minus 0.5 is minus 13, right? So that is also a possible selecting function that will give us this model structure, and thus this model and design matrix. And so that is what this idea is, that you have like this f function, whatever it is, which basically is telling us which model I'm running, right? That's just what this f encodes. I have this data, but I still have to select the data in such a way that I basically get the model matrix I'm looking for, which could be representing either of these possible structures, or even some other ones that I've not listed here. And now this t just means, for some reason, it's defined like this, so that this selecting function would create the matrix in this form, so where like each parameter is one row. So once you transpose this, you get your model matrix, right? That's why you have this t here, the model, the transpose. Once I transpose this, I will get what I want finally. So transposing, oops, let me try this again. Once I do the transpose, I will now get the X matrix basically, right? Which has now what were the rows here are now the columns. So I will have, let's say, the ones in the first column, and then the 20 and 26 in the second column, and so on, okay? So that's the whole idea behind this notation, just in case you wonder when you see it in the lecture notes. Okay, small tangent, let's move on. So just recall where we want to get with this, right? What we want to understand is that when we have this non-deterministic model, which we can write as this phi function, as we just saw, right, where we give it the data, maybe already like pre-processed in this form that we are selecting the specific like effect structure that we want with this f function and then transposing the result. That is one argument. Then we also give it our parameter values for beta and this error term epsilon, which introduces the randomness and non-deterministicness, basically. How can we find values for beta, like for the beta 0, beta 1, beta 2, and so on, which are inside this beta matrix, such that the observed data, the observed y, is as close as possible to the expected data x, like matrix x times beta. Okay, so we can't get it to match exactly in real life when we have a lot of data points but only a few parameters, but we want to find the best solution, right? That's the whole point of fitting a model, of finding the best fitting line in linear regression, for example. And you know, best fitting line is a good keyword because, I mean, we talked also in general that there are like for arbitrary models, you can always use this maximum likelihood estimation technique. But for the specific case of linear models in particular, and when our assumptions like independent and identically distributed data assumptions, or the assumption that the residuals are normally distributed, when those are met, we can use this specific method of least squares estimation, right? So that is what we want to look at today in a bit more detail. So, oops, let me take the pencil that actually writes least squares estimation. We saw it a bit informally in one of the first lectures, but we can also think about it in a somewhat more principled way and try to understand how we can use like its internal mechanisms, like its logic, combined with this matrix algebra, this matrix formulation of the linear model, in order to actually get a very neat and general way to find the best values for beta by just applying a couple of matrix operations. So that's what we are going to see now. To understand why least squares estimation works, we can think of it in a geometric way. Okay, so I'm going to give you a very simple example, kind of dumb toy example, where we can kind of appreciate how this method of finding of minimizing the sum of squared residuals gives us the desired result. Okay, so consider that we would have a data set with two variables in it and just two data points. Okay, so very, very small data set, and y is our dependent variable. It has the entries 2 and 3, and x is our predictor variable, and so x has the entries, let's say 2 and 1. Okay, now with this data set I could use this and try to run a simple linear regression. I will make it even simpler and say that I just want to predict y as a function of just a slope. Like I will fix the intercept to 0. Like I will assume that whatever the line that I want to find is, it has to be anchored at the point 0, 0. So I just want to find y in terms of x. So just one slope beta. I mean, I could call it beta 1 or whatever. I'm just going to call it beta because there's nothing else. Beta times x. Okay, let's call it beta 1 maybe. And then plus some residual error, okay? And I'm obviously not going to find an exact solution, because you can already see that you can't represent 2, 3, like that vector as a multiple of the 2, 1 vector, okay? But we can do our best that we can, and finding the least bad solution using the least squares estimation. So if you, okay, there's different ways in which you could plot these data. One way would be to just say, okay, we do this classical like diagram where we have the x-axis and the y-axis, and here we can see that when x is 2, that's here x is 1, let's say maybe 1, 2, 3 for the values of y, okay. And then where are our points landing? Well, we can see very clearly that this point 2, 2 is here. So there is one data point, and then this point 1x and y is 3, that is here. Okay, so this is our entire data set, just these 2 points, and we want to find the best fitting line, which is constrained that it also goes through the point 0, okay, because we have no intercept estimate here. All right, so we have 2 data points and 1 parameter. We are not over parameterized, right? Because if we have more data points than parameters, even though it's like a very, very simple and dumb example. Right, this is one possible plot we could do, but we could also do another plot which will help us to understand this least squares idea a bit better. So instead of plotting the x and the y axis, we could also say we're going to plot one data point. So data point, I call it dp maybe Latin 1 and dp Latin 2. Okay, so I'm going to plot data point 1, like whatever that value is on this axis, okay, and on the other axis I'm going to plot data point 2. All right. So what I can do on this coordinate system now is I can basically think of either the values of y or the values of x as like a vector, okay? And I could, for example, say that I want to represent. So okay, I need some axis labels maybe. So I'm gonna quickly do 1, 2, 3, and also here 1, 2, and 3. And now I can say, okay, where is my data as a vector on this plane? So I can see maybe, okay, 2 for data point 1 is here, and for data point 2, 3 is here. So my my y vector, like the vector of my dependent variable, is kind of here. And if usually we think of vectors as these arrows, right? So in a way I could say that this arrow represents my data, okay? That's my data, where it has a value of 2 for the first data point and a value of 3 for the second data point. Now I can do the same for x as well, okay? So for my predictor variable, I can say, where's this located on this kind of small diagram? Well, it is 2, 1, so 2 here for the first data point and 1 for the second. So it will be, the like arrow peak will be here, so that's my predictor variable x, okay? Now, what I'm basically trying to do now in this very simple slope-only model is I'm trying to say, what kind of scalar do I have to multiply this vector with in order to get as close as possible to my data y, okay? So if I just have 1 as a beta here, then I would just stay where I am in this place, okay? But if I take a 2, for example, then I would go like twice the length of the vector, but still in the same length, right? Or I could go -2, then I would go in this direction, okay? And I could extend this in principle to wherever I want. And I will have like this very long straight line, which basically represents all the transformations this vector of my predictor variable x can undergo, right? So I could land here or here or here. If I have a very large or negative beta, I can land anywhere, but always on this line only. Like I can't deviate from this one straight line with my predictor data vector, basically. So, okay, so this original vector that has still the arrow peak here, that was my vector x, right? That is representing just the entire data for the predictor variable. And now this straight line, which could go on and on and on forever, that is basically, I mean, I could call it in a way x, if x is now like this matrix form, okay, I could say this is my x times beta. This is basically anywhere I can land using, well, multiplying x times beta on this line, right? I can land anywhere. When I have a big beta, I land here. I have a small beta, I land here. Now, I'm basically asking for finding the optimal value would be to find the value that gets me as close to y as possible. And where is this the case? Well, it's exactly there where I can basically go down like on a line here from y that's perpendicular on this line of all possible x multiplied with beta values. Okay, so here there will be some unique point that I can land on where I have this 90-degree relationship between the peak of y going down to this line of all possible x times beta values that I can land on. And so this point precisely, so like the vector that's basically represented, that has its peak exactly there where the angle between y and this x beta line is perpendicular, is 90 degrees, that is my estimate, my best guess that I have for beta, because here I'm as close as possible to y. Like as soon as I get here, I'm already further away from y. I'm like this far away. If I go here, I'm this far away. I'm really the closest only when I have this exact 90-degree angle, okay? And that's an important idea here. So I can label this vector, like that goes from here up until this point where the right angle sits perfectly. I can actually call it x times beta hat, because that's my least squares estimate for beta. We're going to see in a moment why it is indeed the least squares estimate with this method, okay? But this is where my my best estimate for beta actually lies. Now, as you can see, there is still like this distance between y and this best estimate, x times hat beta. And looking at this general formula, I know that if I go from the basically matrix representation of x times beta, or in this case, well, the optimal x times beta with the hat, plus epsilon, the vector of residual errors, that will lead me to y, to my real observed y. So this line, like this vector going from this point, x times hat beta, to y, to my observed data, that is in fact in this case our residual error vector. Okay, maybe at this point I should make it a bit clearer that this model can also be written in our usual matrix form. So the capital Y matrix would contain the values 2 and 3, and that should be equal to the model matrix, which in this case just has one column, namely the data that are in here for our single predictor x, okay, 2, 1, and that is multiplied with just a single beta predictor, beta 1, and then we should add this matrix which represents our residuals, right? So matrix 2 by 1, which contains epsilon 1, residual for the first data point, and epsilon 2, residual for the second data point. And so this matrix representation can now be abbreviated like this, right? So here, this matrix, that would be equal to capital Y, and this matrix would be equal to capital X in this formula. This matrix would be equal to, there's no capital beta here at least. And this would be this epsilon, which you also see here as a vector. That's what we mean here. So that's the matrix that contains all the residual errors for the individual data points, okay? So just to be clear how this relates to this. All right, now looking at this graph again, we can notice that we can represent epsilon by taking the vector y and then subtracting x times hat beta from it, okay? So we can write epsilon is equal to y minus x times hat beta hat, or likewise it would also be true that y minus epsilon would be equal to x times beta hat, right? These two statements would be equivalent. So once we can represent epsilon like this, that's quite neat, because where we want to get to is now the general observation that x times beta, where whatever beta I pick, it doesn't really matter, that this vector, like it could be this vector or this one, okay, any possible x beta vector I pick, all of them would be perpendicular to this vector epsilon, okay? So what I could write is that the dot product between epsilon and x multiplied with beta, that should be equal to 0, because by the properties of the dot product, it is 0 whenever two vectors are perpendicular. And well, the small adjustment, how do we do the dot product if the two matrices are given as two column vectors, like as two single column matrices? Well, we have to basically transform one of them to transpose it, to transform it to a row vector, so a single row matrix. So we'll do that with epsilon maybe. And then we can use matrix multiplication. And the result will just be a 1-by-1 matrix which contains the dot product result. So effectively what we can state is that the epsilon transpose matrix multiplied with this x beta matrix, okay? We could put the brackets here, but it really wouldn't matter based on the properties of matrix multiplication. That should be equal to the 1-by-1 matrix which just contains the 0, which is just equivalent to saying the dot product between a vector epsilon and a vector x times beta, that should be 0. And that is at the same time nothing else than saying, okay, if I consider these as vectors, epsilon and x beta, then this means that they are perpendicular to each other, right? Which is the case, as we saw graphically here, for any possible x times beta vector that we could pick. And going a step further, I could now say, okay, I have this formula here, but I might as well replace epsilon here by what I've also available as a term for epsilon. So I could say that y minus x times beta hat, that transposed matrix multiplied with x beta. And now I'm leaving the brackets out because that's just something you can do in matrix multiplication. That this should be equal to the 0 matrix, the 1-by-1 0 matrix. All right. And if this is true for any beta I could pick, then this will be certainly also true for the particular beta matrix which just contains ones, okay? And so if it just contains ones, then this won't change x at all. So I could also write that this is just a general case for the more specific situation where I just have, okay, I'm writing this again, y minus x beta hat transposed, and now just times x, because that would be the case where beta is just all the coefficients in beta. In this example, there's just one trivially, so beta 1. If all of the beta coefficients, beta 0, beta 1, beta 2, whatever, would be equal to 1, then this should also hold, and the beta would just disappear here because it doesn't affect anything. So that would also be the case, right? Now, that's an interesting equation because from there we can get to a very important result which we can use to find the optimal beta using least squares. So the important result is the following. I'm skipping a few steps which you can look up in more detail in the lecture notes, but this will eventually give us the following equality after a few more transformations of this equation, namely that beta hat, like the optimal estimated beta values which minimize the distance between our observed and predicted data, those will be equal to the following expression. So it will be x transposed matrix multiplied with x itself, and of that we take the generalized inverse, and then this is multiplied again using matrix multiplication by x transpose, and finally this entire monster is multiplied with y, okay, which is our observed data. So now we have a very neat and general equation which tells us, okay, if we have our outcome data which are given, and we also have our model matrix which basically encodes our predictor data, then we can find the best parameter values by just computing this matrix multiplication. Okay, that's basically the entire machinery now of the least squares estimation within simplified, abbreviated as a simple matrix multiplication formula. And notably, this bit is of particular interest here, like this this matrix, which is like to the left of y here. So that is called the coefficient estimator matrix. And as you can see here, the nice thing about the coefficient estimator matrix is that you can just, like once you have computed it, of course, you can just take your observed data, y, and just matrix multiply the coefficient estimator matrix with the observed data, and it will immediately give you the estimated beta parameter values of the linear regression as a result. So that's a very powerful thing. Basically, we have condensed the entire process of linear regression in this simple multiplication of matrices. Now, seeing all of this, you might still wonder, okay, but where does the least squares part come up, at least intuitively, in this whole process? Like, we've basically now implemented least squares regression as this, in this matrix statement, but where is the squares part coming up? So let me give you the intuition very briefly of where this is related to minimizing squared residuals and why it has to be squared residuals in particular. So here comes the quick intuition of how and why this is actually related to finding the beta values which minimize the sum of squared residuals. So in this graphic, in this very simple example that we have here, you see that we were interested in this predicted data in particular. Like, we didn't want to predict here or here or here, even though we could have had, using different values for beta, we could have landed here or here or here, but we wanted to land here in particular because here we have actually minimized the distance to the observed data. Okay, that's here the smallest possible distance we can have. That's a larger distance, or that's a larger distance, but that's the smallest one we can have. And that is equivalent to saying that once we draw a line from here to y, it should land perpendicularly on this x beta line, okay? So in a different way of looking at this, we found the point x beta hat among all the possible points x beta, which is as close as possible on this coordinate system, where each axis is one data point, which is as close as possible to y, to our observed data. So you can think of this as Euclidean distances, right? You can say, okay, we have some point x times beta hat on this coordinate space, and we have some point y. And, well, how do we compute the distance between 2 points on in this case, just two-dimensional plane, but it will also work for higher dimensional spaces? Exactly, as you remember well from, I don't know, high school, you can compute the Euclidean distance. And how do you compute the Euclidean distance? Well, let's say we want to find the distance between, so I'm going to write distance between y and any particular point on this line x beta. What I would have to do is we'll give it this. This just stands for one specific beta. Could be this optimal one or could be any other one. Okay, x beta prime. So this will be using the Euclidean distance will be equal to square root of what exactly? Well, of the so I take, for example, the y, the first coordinate of it, so the one belonging to the first data point, minus the same thing for the x beta, okay? And then I take the difference between the two and square it, and then I do the same thing for the other dimension, okay? So I do plus y, and then the data for the second data point, so 3 in this case, and then I do minus x beta prime 2, and I square this as well. So I could already replace, if I wanted to, I could replace y1 by 2 and y2 by 3, okay? And so this gives me the, if I take any beta prime, which is somewhere and I compute the corresponding x beta vector for it, then I can immediately compute the distance between it and the y point on this coordinate system. And so as you can see here, just visually, this distance will be the smallest. So the distance will be the smallest when my beta prime, the particular beta value that I picked, is equal to this beta hat, which is like the optimal value, which minimizes the distance to y, okay? So that's just basically the definition of my beta hat. Like that's the estimate I want to find. I want to find the particular beta prime that minimizes this term, which is the square root of this sum of square differences, okay? And here is where the square comes into play, okay? So we see least squares estimation. So in a way, instead of asking about the distance, which will be given as the square root of this sum of squares, I could also immediately think about the distance squared, okay? And then I would not have this square root expression here. But no matter if whether I have the square root around it or I have not, the particular beta that minimizes this term or that minimizes the term with the square root will be the same, right? So just as I could say I want to minimize the distance overall, like which is the sum of these terms, I could also say I want to minimize the squared distance, right? And so here now I'm just left with what exactly? A sum of squares, right? I just have this sum of squares which I want to minimize, and so that is why what we are doing here is precisely just a different way of describing least squares estimation. That's also how you can see that why this square is important, like why we're doing least squares estimation, not just least absolute deviances estimation. It has to do directly with the fact that the squares come from the expression to find the Euclidean distance between 2 points. In this case, between 2 points on this kind of abstract coordinate system, which represents, where each dimension represents a data point, okay? That's the intuitive idea of why this is actually just a different way to express least squares estimation. And also now hopefully you can see why least squares estimation indeed finds the optimal value for our parameters, in this case, the ones encoded in the beta matrix. One thing I want to stress before we move back to RStudio and R to see some more examples of this idea in action is that here I gave you this toy example, right, with this ridiculous simple structure of just 2 data points and one single parameter, like the single slope parameter without an intercept that tried to basically predict these data points. I gave you this very simple example because it's so easy to draw the corresponding graphs. They are just 2-dimensional and everything is easy and nice to think about. But the crucial thing to really take home here is that this is just like one very trivial example of like these matrix expressions in action. But this whole idea, like these equations, in particular the one where we have the coefficient estimator matrix multiplied by the output data matrix, which will give us directly our best estimates for the coefficient, that entire thing works for any kind of linear model, like for the general linear model, you know, like it could be a model with tons of parameters and also even more tons of data points. Well, you know, the typical example of a real world data set. That would all be captured by these general expressions. This is just a very simple example to get an intuitive understanding for the idea. But the logic, the underlying mathematical logic, that extends to an arbitrarily complex linear model with, you know, as many parameters as you want, and also to as large a data set as you want to analyze. All right, so back in R, we can start by loading the so-called language R package. You might have to install it if you haven't already, which is another R package which contains some interesting experimental data, in this case from empirical linguistic experiments in particular. And so one data set that exists in this package is the LexDec package, which is like a data set from some experiment that was run. I'm actually not sure about the context, so there's a reaction time that's a dependent variable. There are various other variables. We don't have to worry about it too much, but what we can do is we can say, okay, we will save this response times as a vector y. That's our dependent variable for our simple toy analysis here. And we have also the frequency of the words. So I think it's actually about, you know, people reading sentences or words, and you want to see if there is like some relationship between the word frequency, which is saved in x, on the that's the predictor, right? And then we have the y, which is the outcome variable, so the reading time, and we want to basically see, is there some kind of meaningful relationship there? And that is, of course, a question we can answer using a simple linear regression, right? So this is not hierarchical data. The data points are independent and identically distributed, so we can just go on to fit a simple linear model. We may call it M0, for example, and we're going to say that's going to be the linear regression with y as the outcome variable and with an intercept, and our predictor x, the word frequency, as the as the effects that we want to potentially estimate. We can run this, and now the next thing we might want to do is extract the design or model matrix, and as with the terminology here, let's for now maybe call it capital X. Okay, so capital X will be our model matrix, which we can extract using the model.matrix command from this fitted model. Let's maybe inspect the first 4 lines of this model matrix. It looks like this. So as expected, it should have 2 columns because there's the intercept, which just is a column full of ones, and then there is the second column, which represents our single slope in this model, which is just basically containing the predictor data. Okay. Now the thing we can do is, okay, here we have the model matrix X, but what we actually want is this very cool coefficient estimator matrix, right? How can we get it? Well, we can just compute it based on this formula. So what do we actually have to do? We need to, first of all, take the inverse. We can do this using the generalized inverse function of this product of the transpose of X matrix multiplied with X. Oops. So that already gives me this part here. And now I have to multiply this entire thing with the transpose of X again. And finally, well, actually, that's already the final result if we would just want to construct the coefficient estimator matrix. So let's save it and call it maybe CEM, okay? Coefficient estimator matrix. Okay, I should have loaded the mass package, of course, which contains the G inverse function, otherwise I can't run it, and I got this stupid error here, so let's try again now. So now I have the coefficient estimator matrix saved. I can look at it if I want, or maybe not the entire thing, but like the first couple of rows. There are some interesting numbers in there. We don't really have to understand why these particular numbers. As you can see, it's quite a huge beast. But the cool thing is now that we have this coefficient estimator matrix, so now we can do a very simple last step to get our least squares estimates for beta, okay? Which is just, well, multiplying the coefficient estimator matrix by our matrix Y, which contains the observed outcome data, okay? And we can write this matrix multiplication here in R using this simple command now, referencing our 2 variables. And let's save the result of this in a new variable called het beta, which will, well, now save our estimates for the intercept and the slope of our simple linear regression. So we can run this and have a look at what het beta now are. So we can see the first number should now correspond to the estimated intercept, which is here 6.58. And the second number in this matrix should now be the estimated slope, right? So beta 0 and beta 1. And if you don't believe me that this magic trick worked, that this really is our estimated parameter values, we can compare this, of course, to the summary of the model output. Okay, so we can do summary of the fitted model, M0. And indeed, here we see 6.58 something for the intercept and minus 0.042 and so on, which is exactly what we also found doing it manually, right? Doing it by computing this coefficient estimator matrix and then multiplying this with our observed data. And in fact, that's actually also what happens under the hood in the LM function, right? So the computational implementation of simple linear regression and also of more complex linear regression models that relies under the hood on this idea that I can just multiply these matrices together as defined here, and this will automatically give me my least squares estimate for my parameters. In this case, just one intercept and one slope, but I could add more, right? I could make it more complex, and this general idea will still hold true. Okay, the last topic that we're gonna look at today is the idea of expected value and variance, and how these two concepts relate to some components of our general linear model. Starting simple from how we can express the expected value and variance of just the residual error, let's say, or express the expected value and variance of the outcome data, the observed outcome data y. And lastly, we are also going to see how we can describe the expected value and variance of our estimator, beta hat, which is, you know, our random variable in a way which estimates our optimal beta values, like parameter values, using the least squares method. So starting simple with the residual term, like remember that here, like this is like the vector containing all the individual residual terms by data point. So in general, for each data point, we can say that, you know, the particular epsilon index I that is just sampled from a normal distribution with mean 0 and some standard deviation sigma, aka that means, in other words, that the variance is sigma squared, okay? And by knowing this, we can just very easily describe the expected value of the residual error, which we will just write as this E symbol, okay? And we will write E, like expected value of our residual error, that will be equal to, well, basically 0, because what expected value means is that it describes the value that this random variable tends to under repeated sampling. Okay, so if we imagine that we would hypothetically draw data points from a normal distribution with mean 0 over and over and over again, like infinitely many times, eventually our sample average will converge to exactly the true mean of this distribution, in that case 0. So we'll write 0, but just as a small caveat, we're not going to write just the number 0, but instead an entire vector with a single column and n rows, where n is the number of data points, or also number of rows of our model matrix X or our outcome matrix Y, which is just full of zeros. This just represents, you know, that we are basically having this expected value not just for a single residual error for the like second or third data point, but for all data points, the expected the residual error and it like the expected value of the residual error is 0. Okay, so this will have n rows, this matrix, like n entries. And for the variance of this residual error, we would have to write, well, variance we would usually write with this capital VAR. And here, if we take the variance of like an array of data points, or like random variables in a way, instead of just like a single one, here again we have like this matrix form now. So instead of just writing as I would for just a single like random variable for just one data point, I could have just written sigma squared, right? But here I'm actually describing the variance for all the data points conjointly. And to do this, I will multiply this with the identity matrix for the nth dimension. You may ask why. Why couldn't we just use because this, you know, this will be this squared matrix now, where I have sigma squared here and sigma squared here and sigma squared here and so on, up until I get to point like to the dimension n, to the nth row and nth column, and all the rest in this will be zeros. The reason why we have to do it this way is that this matrix could, in principle, also be a so-called variance covariance matrix. So that's something I can specify whenever I'm talking about the variance of like an entire array of random variables, as is the case here, where I talk about the array of data points, okay? And so what this comes down to is that here we are lucky, we just have variance, but all the data points are, as we assume in a linear model, independent and identically distributed, which is another way of saying that there is no correlation between individual data points. Like the data points are completely independent of each other. And that's why we can specify this variance covariance matrix very sparsely by just leaving everything as zeros, which is not on the diagonal. If we had some like covariance between data points, in that case, we would also have some other values except for like not non-zero values on the off diagonals. But here, because we are just specifying the variance for the residual error for a general linear model where we have this IID assumption, the variance covariance matrix will just look as simple as this. It's just a diagonal matrix where everywhere on the diagonal we are just repeating the variance term over and over again, so sigma squared. So that's the entire story as far as the variance for the residual error is concerned. Now we can also look at the variance of the overall observed data and also at their expected value. In this case, the expected value, let me maybe make some space here again, would be just X matrix multiplied with beta, right? Which in a way makes sense, right? Because once we've accounted for the residual variation and its expected value, which is 0, the only thing that's left to express y is exactly x times beta. So logically, the expected value of y will then also just be x times beta. And as far as the variance of y is concerned, here we would have to write the following. So the variance of y is actually also nothing else than the variance of the residual error, because the only thing that's not like deterministically begotten here, like the only thing that's random in this term is this epsilon. Okay, so by consequence, then the variance of the overall data y under repeated sampling would also be equal to the variance and then this multiplied with the identity matrix for the particular dimensionality of n, which is just the same as the variance of the residual error. Like we can refer to the variance either as the variance of the data or as the variance of the residuals. It's the same thing because it's the only thing that's left varying after we've accounted for this linear relationship that our linear model describes. Now, the last thing and actually most interesting thing we want to look at here in this context is the expected value and variance of our estimator beta hat. Okay, so the estimator which gives us the estimates of our beta parameter values using the least squares estimation method. And so the idea here is that you can also think of this beta hat as well as this sort of estimator as a random variable, not just a single estimate you get just for one occasional data set. But you can think of this beta hat as like this random variable that describes how we get these least squares estimates under repeated sampling. Okay, so the idea is, imagine for a moment, we already know the true beta values, like for our linear model, the true intercept and slope and whatever is in there. And now in this, given these true parameter values, we would sample data from the population in which these true parameter values are, they are basically fully describing the data generative process in the data that we get from the population. And we would sample over and over again. And each time we get a data set, like a sample from a population, then we would, run the same linear model in order to estimate the true beta, which is, true in the population somehow, but which we only can estimate using this least squares estimator beta hat. And so the idea is then, okay, assume for a moment we have this universe where there is this perfect linear relationship defined by some beta, but of course also some non-deterministicness to it because of some error term. if we are in this universe and we are getting data over and over again, and then we are estimating the beta value using our beta hat, what expected value does this beta hat have, and also how much does it vary between the different iterations of sampling over and over again from the population? And this is what the expected value and the variance of beta hat would describe. So let me clear this playing field again. So the expectation of beta hat is, well, kind of trivially the true beta, like the true beta parameters. That's what a good estimator should do. Like, it should be unbiased, and its expected value under repeated sampling should actually be the true parameters, beta. The fact that this is the case here for our least squares estimator is also another way of saying that this is what I just already gave away, an unbiased estimator. An unbiased estimator has this property that it will tend to the true value of the parameter under like repeated sampling. Okay, so far so good. And regarding the variance of this least squares estimator, we would have to write something a little bit more complicated. So the variance of this beta hat is actually given by, well, first of all, the sigma squared, but this multiplied by the following matrix, namely the matrix X transposed times X and the inverse of the, so the inverse of this, okay? This is our variance, which is actually a variance-covariance matrix for the beta hat, okay? And as opposed to the variance for the residual errors or the data, this is actually a full non-trivial variance-covariance matrix. At least it can be in some cases. So you would not only have, if you would spell this matrix out, you would have something on the diagonal, yes, but you would also have some terms which are non-zero somewhere on the off-diagonals, because this matrix will also describe the possible correlation, like the covariance between different beta parameters. For example, if I have beta 0 and beta 1, like an intercept and a slope, then it could be that in some cases and some types of data, the estimates for the intercept are correlated with the estimates for the slope. If you want to see a full derivation of how we get to this particular term in order to describe the variance of the hat, of the beta hat, basically, of the beta estimator, I can refer you to the lecture notes. There you will see this explained in some more detail, like how we get there using facts that we already know, but here for brevity I'm going to leave this out in the video lecture. The last thing I want to do here before we are done for today is to show you an example in R again using this Lex deck dataset with the word frequencies and the reading times, and just to show you how the linear regression that we ran there, how we can take this model and then also look at the variance-covariance matrix of the corresponding beta estimators. So recall that this was our model M0. I'm showing you the summary again with these estimates for the intercept and the slope of this relationship between the frequency as predictor and the reading time as an outcome. And now what we can do is we can try to compute this particular term, which will give us the variance-covariance matrix. One thing we cannot do, obviously, is we can't use the true sigma. Like, we don't know this. We don't know what the true sigma in the population is, the true standard deviation, and likewise sigma squared, the true sigma squared, the true variance in the population. But we can use the estimate for sigma that we can get out of this model. How do we extract it out of this model? We can actually use the summary command again, M0, and then write $sigma. This will access the estimated sigma of this model. And so we're going to call it hat sigma because it's just an estimate, right, strictly speaking. And we're going to save it. So my estimated standard deviation, like I could also write it S, you know, remember some lectures earlier, is 0.235. And now I can use this and plug this into this formula to get like an estimate for the variance-covariance matrix of the beta estimators, okay? So what we can do is we can write, well, what we want to compute is this times this. So we can write hat sigma that squared, because we are, you know, taking the variance now and not just the the standard deviation. And now this times simple multiplication, because it's just a scalar value, times this term here, like this was the inverse of the transpose of the matrix X, and this again matrix multiplied by X itself again, by the model matrix. So this would be our variance-covariance matrix, at least estimated based on this particular data set. So we might call it like het var, capital V, and gonna save it in this variable. And we can also give us ourselves an output of what this is. So this is now our resulting variance-covariance matrix. And the way to read this would be to say, okay, here I have this matrix, in this case a 2 by 2 matrix, because I have two parameters, an intercept and a slope, to estimate in this simple linear regression. So this is going to be the so-called variance-covariance matrix for the estimators of the intercept and the slope, like of beta 0 and beta 1 hat. And this is equal to, if you like decompose it into what's in there actually, the following terms. So in the upper left corner of the matrix, we actually have the variance for the intercept estimates, which I can write sigma hat beta 0 squared, beta 0 in this case the intercept. In the lower left corner I have the same thing but for the slope estimates, so sigma hat beta 1 squared. That's the variance for the estimates of the slope. And now in the two remaining cells of this matrix, I just have the so-called covariance term. So the covariance term can actually be expressed as some estimate for the, you could think of it as a parameter rho, which is like the correlation between the intercept and slope estimates times the standard deviation for the slope estimates, and then times the standard deviation for the intercept, the other way around, the intercept estimates times the standard deviation for the slope estimates. And so that's what goes in there, and the same thing also on the other side. So it's kind of symmetric in that sense that here you would also have to put the covariance term in, which you see also here that this number is the same as this one, right? Which reflects exactly this covariance term in the variance-covariance matrix. So let me write this out fully again. And so the last thing we can do using this information, where we now have expressed what our estimated variance-covariance matrix is. So in a way you could also again write this as like het var, because it's not the real variance-covariance matrix, just the best we can estimate regarding the variance of the beta estimators. And okay, so the last thing we can do is, as I wanted to announce right now, we can try to find what this estimate for the correlation between the intercept and slope is. Because we have all the information already available to do this, we just need to extract it out of this representation here. So let's do this now real quick. So I can get the estimated correlation between the intercept and slope estimates by taking this value here, which is the covariance term. And so I will access it here using this representation in R. And so here this is, as we just saw, it's actually rho times sigma intercept times sigma slope. So we'll just have to divide away sigma intercept and sigma slope, which can be found here and here respectively. And once we do this, we will then have the correlation term, okay? So let's divide away the square root of this, which is exactly then the standard deviation for the intercept. So het var 1, 1, that's this field here, and then we'll also divide away the same thing but for the slope estimates, so het var 2, 2, okay. And let's do this and let's maybe see what our correlation is. So it turns out that the correlation between the intercept and slope estimators is about minus 0.96, which is a very strong negative correlation, okay? So correlations can range between -1 and 1. 0 means no correlation, -1 means strong negative correlation, and 1 means strong positive correlation. Okay. As the last thing to take home, I want to give you an intuition of what this actually means. Like, what does it mean for the intercept and slope estimates to be heavily correlated? How is that even possible? Let's see this in a small illustrative example. So imagine your data looked like this. You could represent them in this kind of coordinate system, where here you have y, your dependent variable, and here you have x, your predictor, and you want to run a simple linear regression. And now let's say that the most of the predictor values are actually not close to 0, but somewhere maybe around, I don't know what the scale is, 50, maybe it's centimeters, maybe it's body height. Okay, so let's say we are looking at the body heights of different people, and most of the values will probably be somewhere between 150 and 100 and 200 maybe. Okay, so I will have some data points here, and now this will be my dependent variable. Could be weight or something like this, not really important. But the crucial thing is that if this was like a linear relationship that looks somewhat like this maybe, so you could see that there's like something going on that, you know, hard to imagine very well right now, but okay, so if I can see some linear trend which goes upwards here. Okay, so if I now fit the best fitting line, the best fitting line would look somewhat like this. So here it comes. This is all just like approximately drawing, of course, but that would probably be what the linear regression finds here. Now note that the intercept here of the best fitting line would be a negative. Okay, so if I have the values on the dv, maybe that's like some measure of, yeah, I don't know, what would we say, weight. Okay, so that's maybe 90, 60 and 30 kilograms. Okay, maybe not entirely realistic, but anyway. Okay, so here's 0, and now here is maybe minus 30 kilograms, and it goes on to minus 60, and in principle to minus 90, which is obviously not real sensible data, but it's just the principled extension of this y-axis. And now the crucial thing is that the intercept now lands here. Okay, and this is already, so this line is already describing both the best intercept and best slope I could pick. Okay, but now let's say that I would only I would fix the intercept at some other value, just for the heck of it, maybe at 0 or 60 or 90, and I would then still try to find the best fitting slope under the condition that I've already fixed the intercept to some other value. Now what would happen? So if I fix I'm just gonna maybe do it with my hands. Okay, so if I go and fix the intercept at 60, in that case it would be stupid to still keep the same slope, because the same slope would be missing the data by a lot, right? So if I increase the intercept, then in order to still fit the data as best as I can under the constraint that I've changed the intercept, I will have to also adjust my slope, right? So see this motion, this is like the best fitting line, but if I increase the intercept, I will have to reduce my slope in order to still fit the data reasonably well. So, and this idea of I have to increase the intercept and then the slope needs to go down, that represents a negative correlation. Like that clearly tells me that the correlation between the intercept and slope estimates has to be negative, like it's definitely below 0, maybe even close to -1, as we saw in the example on the board, because it matters like which intercept I pick, or the other way around, if I go lower with my intercept, then I will have to adjust the slope and make it higher in order to fit the data. And you can also think of it the other way around. You could say, okay, I'm here and I'm staying at the same intercept, but I change my slope. Okay, then I have to adjust my intercept to like, again, fit the data as best as I can. So as we can see in this example, here the whatever intercept and slope estimates I have will like heavily depend on each other, because you know, if we adjust the intercept and go up with the intercept, we will have to go down with the slope and vice versa. This is typically the situation when our predictor variable is not centered. Okay, it's actually something often not so desirable. So the desirable case is to have the model, this predictor variable coded or like transformed in such a way that you have rho equals to 0. Okay, this will happen once we center the variable at 0, as we will see now. So here I've shifted the y-axis to the average height of these people here. In other words, I have centered this predictor at 0. So in a way, I've like coded the heights, but now with 0 height referring to the average height, okay? I still have units of 1 centimeter maybe, so I have not like standardized it, but I have centered the mean of this predictor variable at 0. Now, everything else is still the same, data is the same, just like the numerical representation is different. But this changes something crucially, because now the best fitting line here has like an intercept as described by where it crosses this new y-axis. And this is exactly at the average predictor value, okay? And so now I should have this desirable situation where the correlation between the intercept and slope estimates is 0 or close to 0, because if I imagine here, now that here I'm at the best fitting line, where the best intercept and best slope are for accounting for my data, and now let's say I move the intercept up, now the best fitting slope in this situation is still the same. Like it doesn't improve, actually it worsens the fit to now go and change the slope. Like because, okay, I've already lost some explanatory power by moving the intercept away from the optimal value, but the slope can stay the same. Like this is still the best solution under these circumstances. Likewise, if I go down with the intercept, then it doesn't make sense to adjust the slope. I'm still having the best slope if I stay like this in the centered predictor situation. Or analogously, if I now change the slope, now and I stay with this slope, then I can't improve anything. In fact, I will only make it worse if I also change the intercept. Okay, and so here with the centered predictor situation, we can see that changing the intercept and changing the slope, so changing the intercept and changing the slope, are two operations that are completely independent of each other. Like when I do one thing, it does not mean that now I have to adjust also the other parameter in some way. And if I am in such a situation, then I will find that the correlation between the intercept and slope estimates, like between beta 0 hat and beta 1 hat, is in fact 0. Okay, so that's the intuitive idea of why sometimes we can see that there is a correlation between the different beta estimators. All right, that was surely quite a lot to digest for today. Briefly summarizing, we looked at the linear model again and found a very neat way to represent it using simple matrix multiplication. And thereby we also got to know the idea of the design or model matrix X and how we can extract the model matrix in R once we fitted a linear model using the LM function. We also thought about linear regression either as like a deterministic or a non-deterministic function, and well, also realized that the usual real-world case is a non-deterministic situation because we can't fully account for the observed data by our linear relationship, so there's always some randomness, some residual error involved in the end. And we found a very elegant way of how we can estimate the best least squares estimates for beta parameters. That could be the intercept and slope and like potentially further slopes in a linear model using, again, simple matrix operations. Finally, we also looked at the expected value and variance for different components of the linear model, and in particular, in the end, of the beta estimators. And we also saw how we can interpret the variance-covariance matrix for the beta estimators, and also understood what it means for the intercept and slope parameter estimators in a simple linear model, let's say, to be correlated. Okay, that sums up everything for today, and see you guys next week in the next video lecture.